लखनवी कोरमा। अज्जा: मटन बगैर चर्बी आधा किलो, चौकोर टुकड़े। दही बगैर पानी के 6 खाने के चम्मच। लहसुन प्याज 3-3 अदद बारीक काट लें। खुश्क कश्मीरी मिर्च 2 अदद। खसखस अदरक पेस्ट 2 खाने के चम्मच। बादाम छिले हुए 12 अदद। काली मिर्च जीरा पिसे हुए 1-1 चाय का चम्मच। छोटी बड़ी इलायची 3-3 अदद। ताज़ा धनिया चॉप 3 खाने के चम्मच। ज़ाफ़रान, तेल, नमक हस्बे ज़रूरत। तरकीब: ज़ाफ़रान गर्म पानी में हल कर दें। आधी प्याज, अदरक, लहसुन, खुश्क मिर्च, खसखस, जीरा, काली मिर्च और बादामों को ब्लेंड करके बारीक सा पेस्ट बना लें। तेल में बकिया प्याज डालकर सुनहरी कर लें। इसमें दोनों किस्म की इलायची, गोश्त और नमक मिला लें। गोश्त हल्के ब्राउन रंग का हो तो बनाया गया पेस्ट शामिल करके मज़ीद 10 मिनट भूनें। फिर दही शामिल करके मज़ीद भूनें ताकि तेल अलग हो जाए। अब पानी डालकर हल्की आंच पर ढककर इतना पकाएं कि गोश्त गल जाए और सब्ज़ धनिए से सजाकर सर्व करें।
Liabilities will be debit, all expenses and losses will be debit. So this is the first rule. What will be debit? Now what will be credit? Increase in liabilities will be credit. Decrease in the assets will be credit. All the incomes will be credit. So this is the credit rule. Now we give some example, and for example we bought goods of rupees 1 lakh from Sham on credit. This is the first example. In this we have obtained the goods. Goods is our asset. So asset, increase in the asset will be debit. So purchase account debit 1 lakh, and from Sham on the credit. So our liability is also increased because we did not pay 1 lakh rupees. So increase in the liability will be credit. Sham account credit 1 lakh. One more example. We bought furniture with 10,000 cash. By paying the 10,000 we have bought furniture. So furniture asset will increase and cash asset will decrease. Increase in the furniture asset. So furniture account debit, and cash is decreased, so decrease in the asset is credit. Cash account credit, this is 10,000. Like this you can pass any journal entry. You must know that increase in the asset will be debit, decrease in the liability will be debit, expenses and losses always will be debit, and all the increase in the liabilities will be credit, decrease in the asset will be credit, and all the incomes and gain will be credit. Okay, thank you very much.
Welcome to this video in which we introduce a class of discrete time signals called complex exponentials. And complex exponentials are actually kind of strange beasts in the sense that they end up looking a lot like sinusoids. So we'll explain why and how as we go through the video. So a complex exponential in general is a signal that has this basic structure, where in the most general case this c is a constant that's complex, and alpha is also complex, and we'll write alpha as e to the r plus j omega, where both r and omega are real numbers. Okay, and it turns out the reason we call this a complex exponential is that we have part of the exponent of e here is j, which is the square root of -1 and makes things complex. So this can get to be pretty interesting. So if we write out what x of n is, again, c, and we take alpha as we've defined it here and raise this to the nth power, we have e to the r plus j omega, and this is all raised to the nth power. And we can rewrite this as c e r times n times e j omega n. So what I'm doing here is I'm using the fact that when I raise something to the nth power, it's the same as multiplying the exponents. And I'm also saying that if I have a sum of two exponents, I can break it up into two sums. Okay, and just because we need something to call it, I'm going to call this beta. I'm going to call the e to the r part beta. And so what I have here is beta to the n. So I can write this then as c beta to the n e to the j omega n. And why do I want to do that? Well, let's start with this e to the j omega n thing. Those of you that have not yet heard of Euler's formula will hear more about it than you really want in a signals and systems class. The idea is that e to an imaginary, raised to an imaginary number, can be written as the cosine of omega n plus j times the sine of omega n. Okay, and again, for those of you that haven't been paying careful attention, j is the square root of -1. I should have pointed that out up here. Unlike mathematicians who use I, engineers, and at least electrical types of engineers use j because I is always current. Now, a consequence of Euler's formula, which we won't really go into right now, but turns out to be extremely useful in many cases, I can also write the cosine of omega n in terms of complex exponentials. So it ends up being 1/2 times e to the j omega n plus e to the minus j omega n. And similarly, the sine of omega n is 1/2j e to the j omega n minus e to the minus j omega n. So anyway, Euler's formula, so I guess I should say these are Euler's formulas because there are several of them, but they show up over and over again and they're extremely useful. So what this means then, this fact that e to the j omega n can be broken into a real part, which is a cosine, and an imaginary part, which is a sine. If I plug this back in here, what it means is that my samples, x of n, are going to basically be this exponentially weighted guy, this beta to the n, times a cosine real part and a sine imaginary part. So this complex exponential actually has sinusoidal components. Again, the cosine real part and the sine imaginary part. So if you graph this, which I have done, this is the sort of thing that you get. Okay, so if beta is 1, so that I have basically, there's a 1 to the n here, but that doesn't actually affect anything. So this is a case where beta would be equal to 1. And what I've done here is graphed the real and imaginary parts of this complex exponential. And you can see that it has a frequency of pi over 4. And the real part starts as a cosine. So it starts at 1, goes down, and hits bottom here, goes back up, and so on. So it does indeed look like a cosine. The imaginary part is a sine that starts here, goes up and down, and so on. So this complex exponential, if I have no constant out in front raised to the n, is just basically a cosine combined with a sine. If I have the case where beta here is 0.9, then the real part looks like this. It starts up here at 1. I guess I shouldn't be coloring in. It starts at 1, goes down, and you can see that the real part, the amplitude of the real part is getting smaller, and the imaginary part, the same thing happens. The amplitude starts out big and then gets smaller. And that's because beta being less than 1, as we raise beta to higher and higher powers, it gets smaller and smaller. On the other hand, if I have beta equal to 1.1, then I start off with a real part that's small and gets bigger and bigger and bigger. Now again, it still looks like a cosine, but as time goes on, the magnitude of the cosine gets larger and larger. And the same thing for the sine, which is the imaginary part. So again, I have an exponentially weighted cosine as the real part and an exponentially weighted sine as the imaginary part. Okay, now given that, well, and I guess I should make this clear. I'm not sure if I've made this completely clear, but this x of n is complex. It has a real part and an imaginary part. And as a complex number, each xn could be represented in terms of its magnitude and a phase angle. So for example, sometimes you'll see it done this way. X of n is a magnitude, which is a real number, and some angle, which is some sort of function of n. Other notations that you might see is mn at an angle of theta n. But the idea is, because it's complex, I can talk about its magnitude and its phase. So if I graph the magnitudes, I get this. This is basically the magnitude of xn. And you can see in this first case, where I just have sines and cosines, the magnitude is always 1. Okay, so the magnitude of this complex number is always 1, or this complex sequence. When beta is 0.9, you can see that the magnitude decreases exponentially. And when beta is 1.1, you can see that the magnitude increases exponentially. So I guess the point of this is just to show that the magnitude of the complex exponential depends on this term, And then its angle, which I've also graphed in the next picture, depends on this term. Okay, so what I've actually got here is the angle. It's sometimes called the argument or the angle. It's basically the angle associated with this complex number. It starts at 0, goes up to pi over 4, pi over 2, 3 pi over 4, and pi, and so on. And what I've done here is graphed, again, the real part, the real part and the imaginary part of xn. And you can see that an angle of 0 corresponds to something that's completely real. An angle of pi corresponds to something that's completely real and negative. An angle of pi over 2 corresponds to a real part that's 0 and an imaginary part that's 1. At an angle of, assuming this would be, let's see, oh here, this would be minus pi over 2 or 3 pi over 2. Either one of those is the same. Again, I have a real part that's 0 and an imaginary part that's negative. So again, the angle is a function of the relationship between the real and imaginary parts. So that pretty much wraps up this video. And at this point you may be saying, well, why should I care? The reason that you should care is that these complex exponentials, these these signals that look like this actually show up all over the place in signal processing. When we do Z transforms, they show up there. When you do discrete time Fourier transforms, they show up there. They basically just show up all over the place. So it's useful to understand them and understand how they work. So I hope this video has been helpful. Thanks for watching.